can share data. Okay, so I'm going to go ahead and pull up my teaching notes, and we'll go from there. Okay, so today we're going to work with standing waves on a string. And let's see. We've got a couple of things we're going to work with. Like we're going to work with the tension on the string, which is just a force. And you'll measure the force with the IOLAB force sensor. And so you'll have the eye screw in your force sensor. And if you haven't done so, go ahead and calibrate your force sensor before we get started. And I'll just keep talking while you do that. Got 3 factors of standing wave. So you've got the driving frequency. So that's what the motor is used with. So you're going to use the motor to vibrate the string. We have to tie the motor to the string, and I'll show you about that. And the length of the string. So they're asking in the online lab manual that the string from where you tie the motor onto the string all the way down to where you tie the end of the string to IOLAB eye screw, that distance is the distance L, and it should be somewhere between 60 centimeters to 70 centimeters. Mine is actually at 71.5 centimeters when I actually tied it all together. Okay, so now, different strings are made of different materials. So I've written this portion because the string that they're using in the online lab manual, we did use last semester, but a lot of those got, when they got returned, they were cut. Of course, that's probably par for the course with the tying of the string. And so I used a different string in your kits. So the string that you have has a linear density. In fact, all strings have linear density. But the linear density is given as 2.88 times 10 to the minus 4th kilograms per meter. So right now, go ahead and write this down in your notes, or you can go ahead and write it down on your Excel worksheet. At the bottom of the worksheet, you have the handbook value for the coefficient of linear density, okay, or the linear density coefficient, as being 2.88 times 10 minus 4, or you can write it as 2.88 capital E, then minus 4. Okay. Now in the online lab manual, it gives the linear density of the string as 2.35 times 10 minus 4. So make sure you don't use that one because you have a different string in your kit. All right, so when it's all put together, and I'll talk about how to put together here when I use my webcam, I'll show you that. But when it's all put together, we're going to allow the motor to vibrate, and that will send waves down the string. And when you have tension in the string, then the waves will travel much better when you have tension in the string. And depending on the tension and the length of the string, you're going to be able to get what are certain harmonics of a standing wave. A standing wave is basically a wave traveling down the string from the oscillator to a barrier, and our barrier is the eye screw of the IOLAB, where it will reflect backwards and go back and forth, back and forth, back and forth. So if you can imagine, on this one side is where the motor is, and on the other side of the string is where the IOLAB eye screw is. And then a standing wave can be set up depending on the amount of tension you have in the string. Then you have a wave going down, a wave going back, and it keeps going back and forth. And when that tension is perfect, you'll get a certain harmonic. And so we have here, for n equals 1, you have this type of waveform on the string, which unfortunately we cannot get an n equals 1 for this setup because it would require too high of a tension, too high of a force. It will exceed the 10 Newton limit that your IOLAB has. So we are definitely not going to try to get the n equals 1. Okay, so X that one out in your head, not going to do n equals 1. But we have a node here and a node here. So we have a node at the motor where it's tied off. And we have a node at the I screw where it's tied off. And for this case, in order to get this n equals 1, you have one antinode. So a node is a zero displacement up and down. So it just doesn't move. And the same thing goes for the other side. But the middle, what's called an antinode, the opposite of a node, is where you have maximum displacement of the wave. So we see here we have one antinode, and one antinode is the same number as the harmonic, n equals 1. Now, if you reduce the tension, or we're actually going to start off at n equals 2, so not n equals 1, we are starting at n equals 2. So you have a certain amount of tension on the string, which will cause, of course, the node is where the motor is tied off at the left end, and the node at the right end is where the I screw is on the IOLAB. And then you'll set up a standing wave such that you have one full wavelength going between the two. Or if you look at this, you have two antinodes and another node in the middle. So we have two antinodes, and the two antinodes correspond to the same number for the harmonic, n equals 2. Okay, so if you then reduce the tension a little bit more, it doesn't take much, but you're going to reduce it a little bit more, then you can get the third harmonic where we have 3 antinodes. And then you reduce the tension a little bit more, and you get 4 antinodes for a standing wave. Now, these only occur for particular tensions, so you have to play around with it a little bit and have good finesse in trying to get these tensions. But once you start getting them, then it's easier to get. Okay, so we have n equals 2, n equals 3, n equals 4. Now, on the worksheet, the Excel worksheet, I actually have places for 4 harmonics. Even though they say in the online lab manual they have 3 harmonics, but I think if we had 4 data points for the graph, then we'll have a better way of getting the slope of the line. So we're also going to do n equals 5. All right, so that would be 5 antinodes for the n equals 5. That's a little bit less tension than the n equals 4, but not by much. Okay. So I say here the driving frequency of the wave is determined using the FFT application. So we have a fast Fourier transform application we're going to use, and I'll show you how to use that. And we're going to record the maximum frequency when using that. So there's a couple of things we're going to measure. We're going to measure the tension, which is the force from the force sensor. That's your tension T. Okay. And we're going to measure the frequency at which the wave is oscillating or vibrating, and that'll give us the frequency. And we'll use those two in an equation along with the harmonic number. And then I'm going to go ahead and go way down the end here and get to the equation. So this is the equation after it's all been manipulated algebraically, where we have the tension is this capital letter T. That's your force on the force sensor. Okay. Then this F right here, that's the frequency at which the string is oscillating at. And we'll get that using the fast Fourier transform application on the IOLAB software. And N is the harmonic number of whichever standing wave that you are achieving with that particular tension T. Okay, so we're going to calculate the ratio of the frequency to mode number for each mode. That's F over N. Okay, so the frequency that you get for that particular standing wave divided by the mode number or the harmonic number for that same particular wave and that tension. So we can see here we're setting up an equation for a linear representation. So if we square F over N, because remember we have that, then the F over N quantity squared represents our x-axis, okay? Because you can see this is y equals the slope times x. So the tension T is the y, so that's going to be our y-axis on the graph. And F over N squared, the whole thing, F over N squared, we're going to put data points in for that, and that'll represent the x-axis. So what's left are the constants. You have 4, the length of the string. Remember, that's the distance between the knot that you tied to hold the motor onto the string, all the way over to the other end of the string where you tied the string to the IOLAB, and that distance should be somewhere between 60 and 70 centimeters. And then there's this Greek letter mu. So that Greek letter mu in a lot of textbooks represents the linear density of the string. okay? It's not the same mu for the average value you have on the force graph when you're using the iOLAB device. They just use mu for that one also. So it's not the same thing. So the tension T, that's the force you get from the iOLAB software, where you're looking at their mu to get the average value. But this mu right here in our equation is the linear density, which we're going to try and determine by taking data and comparing it to what I told you up here, that your handbook value is 2.88 times 10 minus 4. So that's your linear density handbook value, or theoretical value if you want to do it that way. Okay, so back down here, I say caution, the force curve has a maximum of 10 newtons. Do not exceed 10 newtons. Of course, the n equals 1 would exceed 10 newtons. We're not doing n equals 1. We're doing n equals 2, n equals 3, n equals 4, and we're going to do an n equals 5. So n equals 2 has 2 antinodes. N equals 3 equals 3 antinodes. N equals 4, of course, is 4 antinodes, and n equals 5 will have 5 antinodes. All right, so when you get it all together, so you've got this string, and one side of the string is tied off your tabletop. I've got mine tied to the leg of my table, and it anchors it so it won't move. So this side is tied off. It doesn't move. And I'm using a book, a hardback book, to raise the string up. So when we have this motor, which is tied to the string, is lifted up from the tabletop, and then you have the rest of the string, which is about 60 to 70 centimeters. So from the motor where it's tied off that knot, all the way over to where it's tied off on the eye screw on the iOLAB, that length is supposed to be 60 to 70 centimeters. Okay, then you got that tied off. And you're going to put one hand on the iOLAB, and you're going to push it away from the motor, thus increasing the tension in the string. And you have to hold that iOLAB with your hand so it doesn't move when taking data. So once you have a particular standing wave, let's say for n equals 2, then you have to hold it and take data with the iOLAB software. And I'll show you that too. Okay, so we got measured length L meters. So that if you measure 65 centimeters, then that's 0.65 meters. And once you have the motor tied to the string and the iOLAB tied to the end of the string, you will collect data. Okay. Now here, start gently moving the iOLAB device away from the book or away from the motor, increasing the tension in the string. Watch carefully for a standing wave to appear. You might actually pass right by seeing a standing wave if you go too quickly. Once you see a standing wave, hold the iOLAB in place for a couple of seconds while you're holding the iOLAB, count the number of waves on the string and determine which harmonic this is. Well, you probably go directly to the n equals 2, then after that n equals 3. Stop taking data and determine the average force. Okay, so this is a screenshot that I did a couple of days ago, where if you're starting off with no tension in the string, then you start building the tension up by pushing the iOLAB away from the motor. Then you get a certain standing wave to form, and you hold it there and keep it there, keep it there, keep it there, and then you release it. Okay. Then of course it's during this portion that you are interested in holding that particular tension for that particular harmonic of standing wave. And then we're going to use the fast Fourier transform application to determine the frequency. Okay. So in this force graph, you have the force versus the time. You can see here, now don't get confused with that mu, because you already know that mu in the iOLAB software means average. So when I was doing this, I had an average of like 1.908 newtons. And you don't have to worry about the negative sign. It's just negative because we're using the force sensor and we're pulling instead of pushing. Okay, so it's that positive value for the force. Okay, so you get the force from the iOLAB software, and we're going to use the fast Fourier transform, which I'll show you how to do, and we'll get a frequency. You want to use that frequency and the mode number you are achieving, the harmonic number you're achieving, and that force, and we'll start plotting data. And from a linear plot of the data of the force tension versus the ratio of the frequency to the harmonic number squared, then we can get that. Okay, so we'll determine the linear density of string by experiment and compare it to the handbook value. Okay, continue finding other standing waves for other harmonics, making sure that you do not exceed 10 newtons, that's your limit, and force on tension of string. Record the corresponding tension, and there. So I'm sure people are asking about screenshots. Yes, you're going to do a screenshot per harmonic number. So if this was, let's say, a harmonic n equals 3, let's say, then I will have this up, but I also have the fast Fourier transform, which will appear underneath the force graph. I'll show you that. And then you'll take a screenshot showing the data. And so you're going to have a screenshot of that for n equals 2. You'll have another screenshot for n equals 3, another screenshot for n equals 4, and a final one for n equals 5. So you have you'll have four screenshots from n equals 2 through n equals 5. Okay. So you got to record the corresponding tension, force, and frequencies in the Excel worksheet. And then we'll calculate the ratio of frequency to mode number or harmonic number, ratio of the harmonics or modes, then square these values, record them under the heading of f over n squared. And then plot a graph of tension, T, that's the force, versus the f over n squared, that'll be the x-axis, and determine the slope of the line, the linear trend line. And from the slope of the line, determine the linear density. So when you finally get the slope value, that should equal 4L squared mu. So you take the slope and divide it by 4L squared, and the result should give you the linear density mu. Okay. And then you also want to answer all the questions that are in the online lab manual, including the results section. So in the results section, you'll do a comparison, like how well did your linear density value through experiment compare to the handbook value. And I want to remind people, because there might have been some people that came in late, that your handbook value is this 2.88 times 10 minus 4 kilograms per meter. So you just write in 2.88 E minus 4 in the appropriate box on the worksheet. Not the 2.35 times 10 minus 4 that they give in the online manual, because we're using a different string that they're using. Okay, so I'm going to go to the Excel worksheet and go through it that way. Let's see here. And then we'll get started taking data. Well, and setting up things, then start taking data. Even though I'm going to talk a little bit longer than usual, I want to make sure everything gets set up right and how to set up the wires for powering up the motor. Okay, so here we have the worksheet. And length of string, see, I was just putting my number in there, but you'll put it in yours. If you had measured 65 centimeters, then you would type in 0.65 meters. Or if you had 62 centimeters, then you have 0.62 meters. That would go in there for the length. And here are the harmonic numbers. So it's going to be 2, 3, 4, and 5. So write those down in your Excel worksheet right now if they're not there already. So you're doing 2, 3, 4, and 5. And then we're going to do, this is where the frequency will go when we use the fast Fourier transform. And then the frequency over the harmonic number is just that. You take this number, divide by that number, and you get that. Then over here, this is going to be the table for graphic. So whatever you get for the ratio of F frequency to a harmonic number, you square that number and put that there. As simple as that. This is going to be the square of that number. And this is going to be the force, tension T, that you get from the IOLab software for the force. We're going to take an average force. So, and then you're going to graph all those data points onto a graph here and get a slope. Now, then you'll just go ahead and record what the slope is from the graph. And make sure it's more than one significant figure, because Excel is notorious for that. They'll give it to you like in a general number in a category. So you probably have to, once you get the equation, you probably have to right-click on the equation and then format trendline label, and change it to scientific, and give it like 4 decimal places. Okay, then that will be the slope right there. Then take that slope and divide it by 4 times your length squared, and that will give you the calculated linear density mu. And then you'll compare it to this 2.88 times 10 minus 4, which is the density of your string. Then you'll do a % error calculated. And when you get that, then you go ahead and write up your live report and results section, comparing these two together using that % error and answering any questions you have in the online manual. Okay, so I'm going to stop sharing that. And I'm going to go to, let's see here. I'm going to pull up my ILab software. If I can find a good one. Let's see here, going through my files here. Okay. Okay, so in this one, I actually, before I started recording for the data for the force probe, okay, so I got the force probe there. What I did was I set up the standing wave, and then I started recording. I didn't like start recording, then play around it with trying to get the standing wave. I got the standing wave first, and when I was happy with it, then I started recording and got the force. And so this is the force that I found. And I just kind of did it for like 5 to 6 seconds. That should be good enough. Then all you do is, highlight the area, and you'll get an average value. So for this one, that was 1.308 newtons. Okay, so there's that. But in order to get the frequency, so there's my tension force right there, 1.308. That's my tension, the positive value. Then how to get the frequency? All right, down here in the toolbar, click on that square with the arrow sticking out of it. You left click on that, and then you move over to the FFT. If you move off, it'll go away. So you have to re-click on it and then move straight on over to where it says FFT in the drop-down menu. Then go down and choose the 1024 bins that are being generated. So you click on that. Then you kind of go right up into it, and you see you have this little gray band that comes up. And you have this black line which you move around with your cursor. If you put the black line within that gray band and left click once, don't drag, just left click, then you can move it around. And you can see down below in the fast Fourier transform, notice that instead of a time axis, we have a frequency axis. So those are all the different frequencies that the fast Fourier transform is trying to work on all this. And you notice that there is a definite peak. There are some other ones we're trying to form, but there's a definite one which is really tall. So you would then put the black line centered onto that peak, and you see the V, it says 220.032 hertz. That's the frequency. I don't know why it's a V. It might be trying to make a Greek letter nu, which is sometimes looks like a V, which sometimes is being used as frequency, but that's your frequency, where it says V colon, then 220.032 hertz, and the HZ kind of gives away to hertz as a frequency unit. Okay, so there you have your average, and there you have average force, there you have your frequency F. And that is for whatever harmonic number that I was doing this for. And so I'd have an N for that too. So that's how you get the frequency. And if you have any problems with that, you can always share your data and I can try and figure it out. Okay, I'm going to stop sharing that. And we're going to go to setting up the equipment. All right, so let's see. So here I've got the blue cylinder, which is your motor, and it has this red and black lead coming out. And I've already glued the end, so we try to reinforce those wires, as they say on the online manual. So you have to be careful with that. So you don't want to tug these wires too hard because then you'll damage the motor. Okay, and you can't fix it. But what's really interesting is that the ends of the leads, the wires are really, really thin and there's not much sticking out of the plastic casing, but we're still going to be able to work with this. We'll just follow the instructions they had on the online manual. There's just enough of the exposed metal wire coming out of the ends, we can still work with that. Now, in the online manual, it had a technique to wrap the string like 2 or 3 times around the cylinder, very, very tight, but you want to make it tight. And then it did something like they twisted, made bunny ears and put a loop around it and then pulled it tight and it was supposed to make a knot. I kept trying that and it wouldn't work. It would just keep coming off, kept coming apart. So I wound up and I hadn't tied the other end yet. It was still loose. So I wrapped it a couple of times and then I tied a square knot. Then I tied it a couple of times, wrapped it another again and tied a second square knot and getting that really snug so that it's on that string tied. So I had to use a square knot, not what they were doing in the online manual. Okay, now the other end of the string, if you can see, it's going off the end of my table. Underneath here is the leg of my table, and I've tied the string, see that? I've tied the string to that leg going off the side of the table. So it's anchored really well, it won't move. Okay, then once I got that, then on the iOLAB, I then tie the other end of the string to the eye screw. And that distance, and I still have I didn't cut the string, so I have this extra just kind of sticking out there, which is okay because it just goes off the side. So this distance between, I'm going to just kind of draw it out here, so I'm going to go off camera here. So this distance here from the eye screw all the way over to the knot on the motor, I've got that supposedly between 60 and 70 centimeters, but mine turned out to be 71.5 centimeters. So I measured that, and I have enough length here on the edge of my table between that and the motor. And I'm going to take a hardback book, and I'll set that there, and I'm going to open it up, and I'm going to put the string into the book and enclose it on top like that. And then if you can see here, I only have about a finger's width, so the motor's not touching the book, but I still want that string to be just short enough on the book side. And it's kind of tight there. Okay, and it will drop down because I won't have any tension on there. And that does that. Then I took a second book and put it on top of that book to kind of weigh it down. So now I've trapped the string and I've got it elevated so that when I actually put tension on the iOLAB, and here I'll put tension on it, you see that it elevates the motor from the tabletop so it won't touch the table while it's vibrating. All right, so then you see here I've got this string all the way here. I've got some blue tape here so you can see the string better. So I've got a white tablecloth here. All right, so I've got that. So now I've got that. So how to hook up the power. All right, here we go. Now I've got a long breadboard. You have a short breadboard. That's okay. The short ones still work. And you should have a couple of jumper wires. Okay, a jumper wire is just like the wire, plastic coated, and it has the metal wire sticking out of both ends. You got these little black plastic caps that help you hold it. And then the holes in the breadboard might be a little stiff because they're fairly new. You could take the jumper wire and kind of poke it in to the holes that you're going to use to kind of loosen up the metal contacts inside. So I just did that a couple of times. Kind of loosen things up. Okay, now here's the idea. You have a battery case. No, color is just color. It has no bearing whatsoever on a wire. I mean, if you were a designer and you want to make sure you had certain connections, then you would worry about color. But not with us, it doesn't matter. But when it comes to the battery case, now the jumper wire doesn't matter. Doesn't matter. I've got a yellow one and I have a blue one. Okay, but the red and black wires on the battery case do matter. Okay, the red is going to be the high side, high voltage side of the batteries that are in there, and then the black side is like the low or the ground side if you want to do that. Okay, so red and black on the battery and red and black on the motor do matter. Okay. So I'm going to take the cover off. You see I don't have my batteries in here yet. Makes it easier. I don't have a lot that weight in there. And then I'll move this over a little bit. Okay. So if you notice on your breadboard, you have like a left side and a right side, and there's a center groove going down the middle. Okay. And you have these numbered rows and you have these lettered columns. Okay. A numbered row on one side of this groove are all connected electrically. So if you were looking at row number 10, those 5 holes in row number 10 that are together are all connected together. You also have like holes on the far left and far right side. There's far right, far left. And we're not going to use those. We're just going to use these 5 holes. Well, not all of them, but we're going to use a row. We're going to make our connection. So what I'm going to do is I'm going to have the red wire on my battery cage to be on one side of that center groove, and the black wire of the battery cage to be on the other side of that center groove. So I notice that the wires are a little bit thicker, but they still don't have much. It's like maybe a millimeter or 2 of the actual wire, metal wire sticking out, but that's good enough. So I'm going to find one of these rows, doesn't matter which one. I'm going to put, if I can get that in there. That metal wire into one of those holes. And I've been doing it for the past couple of days and I didn't have any problems with it. Okay. All right, so there we go. So I have that in one of the rows on one side of the groove. Then the black wire, doesn't matter which row you pick, is going to go in one of the rows on the other side of the groove. Okay, so you see that? So you have red wire on one side of the center groove and a black wire on the other side of the center groove. Then you take a jumper wire, okay? And let's say for the red wire, in the same row, okay, I'm going to put one of the jumper wires. So you see that? So I've got a jumper wire and the red wire. They're in the same row, like right next to each other. And then another jumper wire for the black wire on the other side, again, in the same row as the black wire is in. If I can get this in there. And twist that off to one side. Okay, so there's the black wire, and there's the jumper wire. They're in the same row on the other side of that groove. Oh, there goes my black wire. Put that back in. Okay, does everyone see that? Okay. Now, to make a connection to the motor. So put your breadboard very, very close, like the end of the breadboard, very, very close, because you don't want to stretch the black and red leads off the motor. You don't want them to be tight. You want them to be kind of loose, hanging there, but still into the breadboard. So what I'm going to do, and then notice that the leads are really thin, and this is the technique they have on the online manual, is that here's my jumper wire. The yellow one I've got connected to the red wire of my battery case. And I'm going to use the other side of the jumper wire to trap the thin metal end of the red wire of my my motor into the breadboard. So I'm going to place in a different row, okay, a different row, maybe closer to the edge of the one end of the breadboard. I'm going to put it into one of the holes and hold it there, and then take the jumper wire and put it in the exact same hole that I'm putting the red wire, if I can get you to see that. Kind of hard because I don't have much room here. Okay, so I've got my red wire. Nope, can't move that. Being trapped by my jumper wire, and the other end of the jumper wire is connected to the same row as the red wire to the battery holder. Then we do the same thing with the black wire on the other side of the groove. So red wire is on one side of the groove, black wire is on the other side of the groove. So I'll place that into a row, different from the row of where I've got the other end. Then take the jumper wire connected to my black wire, and then put it in the exact same hole I've got the wire for my motor. And then those leads coming off the motor are not stretched out. I'm giving it some room to play. Get that back in there. So when it vibrates, it won't vibrate out of the holes. And it might take a couple of times to make sure you have good connection. Let's see. I don't think I can show it close because I've got this huge breadboard here. It's kind of hard to get my webcam around there. Maybe you can zoom, but here I've got, there's the red wire being trapped by the jumper wire connected to the red wire of the battery. Okay, there's the red wire of the battery. There's the red wire of the battery. Here's the jumper wire in the same row as the red wire of the battery. And then another whole set of rows. I'll put the red wire of the motor, and I'm trapping that really thin end of the motor with the other end of the jumper wire. So I've got the red wire of the motor attached to the jumper wire, and the other side of the jumper wire attached to the red wire. So it's red wire to red wire for the battery to motor. Same thing with the black wire. So here's a black wire being trapped by this other jumper wire in the same hole. And then over here, the jumper wire is connected in the same row as the black wire for the battery. So when I go ahead and put the batteries into the battery holder, and it's the flat end to the spring end, so the flat side goes into the spring side. Okay. Now make sure that the switch is off on the other side of your battery holder before you put the batteries in. And when I turn this on, can you see it vibrating? And you can see there's like a wave being formed right here. Go ahead and move this. So there's a vibration going on. If I'm down the end, I've got my hand on the iOLAD, and I am moving it away from the battery, from the motor, until I get more and more attention on it, and I can get a standing wave to form. Can you see that? I've got an antinode here, and there's, I moved it, and a node right there. And of course, there are more down the line. If I change the tension again, I can get another harmonic to appear. It might be difficult to see because it's moving back and forth so much, but I've got a standing wave like this, and you'll see it when you actually put it together. But you have to make sure you have your motor connected to your battery pack so you can get the vibration. So go ahead and spend some time getting that hooked together. And then I'm going to turn this off. And back to me. Okay. All right, so the jumper wire color, again, with Ben, doesn't matter what the jumper wire color is, but the wire coming out of the battery cage and the wire coming off the motor, you got a red wire of the battery cage, has to be electrically connected to the red wire of the motor using the breadboard. And same thing for the black wire coming out of the battery cage, you're having it on the other side of the center groove. And those are all connected together. So the black wire of the motor and the black wire of the battery cage are electrically connected using the breadboard and another second jumper wire. So see if you can all get that connected and get the motor to vibrate. And when you've accomplished that, write done in the chat. And Joseph's done, great. Matthew, okay, Nathan and Matthew got 3 done. Just 9 more people to go. And Tyler's done, great. And Brad, I'm pretty sure I have it hooked up right, but it isn't turning on, okay. Having trouble getting a standing wave. Justin, right now, I want to make sure that everyone has the motor working. Okay, so we've got Justin, got Jacob, got Kimberly, but Brandon's having a problem. Brandon, go ahead and try, using different holes on the breadboard and make sure that you're actually trapping the metal portion of the wire sticking out of the motor in contact with the metal portion of the jumper wire inside one of the breadboard holes. So just try and rewire again, see if it'll work. Ethan's done. You got Joseph, Nathan, Matthew. Tyler's 4. Justin is 5. Jacob is 6. Kimberly is 7. Ethan is 8. So Brandon's still working. That's 9. So we have 3 more people to write in the chat. That's great, Brandon. Thank you. Ben is still working. Wire keeps falling. I understand that. One of my TAs actually taped the wires from the battery cage down to the breadboard to keep it from coming out. So they stuck the wire in, then bent it down, then put a piece of tape on top of it. Maybe that'll work. If that's that's popping out, is it the battery cage wires popping out of the breadboard, Ben? Yes, okay, yeah. So you can get them in there and then kind of fold the wire down a little bit, but to keep the metal portion in the breadboard and put a piece of tape across to hold it. Tara, got it. Great, Tara. think that's most everyone. Ben is still working on his. There might be one other person I didn't see yet. But everyone else who has it working, make sure that you have tied off the other end of the string at least 60 to 70 centimeters away from the knot on the motor onto the eye screw of your iOLAB. And then go ahead and use the tape measure to measure that more exactly. And then you'll measure in centimeters, then convert that to meters and write that down as the length in which the standing wave is going to occur. And then go ahead and try to achieve the n equals 2, where you have the one antinode in the middle and the two antinodes either side. And it will probably occur somewhere around 5-ish newtons of force. It all depends. So see if you're getting something close to 5, and then see if you can get that to work. It's not exactly 5, it's kind of around 5. And hopefully everyone has enough space on their desk or table that they can, this is going to be like close to a meter long of work space you have to have. And if you don't, then I had a student yesterday just put it on the floor and then tie the string to a table leg to anchor it, and then set everything up on the floor. Even if it's a carpeted floor, it should be fine. I've got my iOLAB flipped to the side where the felt pads are down, because I find it easier to hold it when I'm taking data, because once you get that standing wave set up, you have to hold the iOLAB still, that same tension the entire time you're taking data for the force, the tension. You can't just let it go and take data, because it will slip. So you have to hold it in place while you've got that standing wave for that particular harmonic. Take the data and stop taking the data. Then you can let go of the iOLAB, and then you can find the average force and find the frequency using the fast Fourier transform. Take a screenshot, and then do that. So Ben is done with that, and then Matthew says, how do we get the two harmonics again? You have to turn the motor on, and then put tension on the string, and then move the iOLAB away from the book and motor, and then you're increasing the tension in the string, and you should start seeing waves form. And you could turn the iOLAB software on and watch the force change. And in fact, if I do that, let's see here. I have a suggestion. Okay. We got the force on. We got the force, so hopefully people can see this or are interested. And then notice how it goes from +5 to -5. So if you go to this y-axis settings, you can click on that, and I will change the 5 to the min value from -5 to -10. That way you can actually see 5. And then when you go to record, then you're pulling until finally you get that n equals 2 to occur. And then you can take the data and hold it still. And then you can go ahead and hit stop. And then go back and then just choose that portion if you want to do that. I didn't have my motor on, so I can't get the frequency, but that's kind of the idea of like heading towards around 5 and looking for that n equals 2 harmonic. And Connor, I understand. I think I have a backup plan for you, but I'm hoping that you can still work on it and get the motor to work. So keep trying that, Connor, and see if you can get it to work. And then if it still doesn't work in the next like 10 minutes, I have a backup plan. And then Justin, we just have force selected for the IO-Lab. That's right. You only have force. That's right. And you're welcome, Connor. And then Matthew O'Neill. So n equals 2 is at approximately -5. Yeah, it's around there somewhere. You might get an n equals 2 at a far lesser force, Matthew and everyone else. And I think that's because the string doesn't have enough tension on it, and the motor is like flopping around in another mode, so it gives kind of a false reading at a much smaller force value. So definitely check around the -5 Newton region and see if you can get that 2 antinodes to form and a nice sharp node in the middle, and then hold it and then take your data for the force, and then also find the frequency using the fast Fourier transform. And Justin, I had it like about 4. I mean 4 antinodes, Justin? Oh, -4 newtons. Okay, 4 equals 2. That may be. I mean, go ahead and do that. So I would say it was kind of close to 5, but not exactly 5. So go ahead and make the n equals 2 harmonic sending wave form, and there should be a point where the antinodes are like their fullest, and then you hold that and then take data. And if it's around -4, then it's around -4. But mine was closer to -5. It wasn't quite at -5, but it was on the -4 side, but closer to -5 than -40. And Tyler, I'm getting a result way over 5 newtons for most of the wave types. And then Joseph said I got -6.5. Is that too high? Well, if you're getting the n equals 2 waveform to form, that may work for your string that you have. Not sure. It could also be depending on how long your string is to get that waveform to form. And of course, because if you think about the equation, you've got T equals 4L squared mu multiplied by that frequency over the harmonic, both squared. So the frequency is going to stay the same approximately, and you've got n equals 2, and your length is a little bit shorter, then you have to have a bigger tension to make it work. And then, so yours is larger than 70 centimeters. Okay, so kind of like mine. So I'm thinking that 6.5 might be too high. Yeah, see if you can like play around with the tension and get that. And then Tyler's is 6.63 meters, so that's on the shorter side. So I can see that you get maybe a little bit higher than 5 newtons, but when you say way over 5 newtons, what do you mean, Tyler? Is it like 5.1, 5.2, or is it more like 8 newtons? What do you mean by way over 5? Like 6.8. So that's kind of close to what Joseph is getting. Okay. But since yours is a shorter string, I kind of think that's possible. Because, in the equation, if you have the L go down, that means the tension, the L goes down, that's an equality. And that frequency. So actually, the tension should go down if you have the L go down. If you have the L go up, then you have a higher tension, where everything else would be Okay, so I'm thinking maybe Joseph's is right and Tyler's is a little bit too high. But go ahead and both of you play around with it, going back and forth, because things might need to settle in because you're stretching that string, and then the fibers might adjust on you. Kind of go back and forth a couple of times, and then see if you can get it to settle in. So try n equals 2 again, and see if it will change on you for the force. Because those fibers will probably, as you're stretching it, might kind of get closer together as you stretch it, and set itself a little bit better. Okay, so work on that. And I need to go back to Connor. Any luck, Connor? Not yet. Okay, keep trying, and I'll see what happens. And you're getting around 8 newtons of force on n equals 2, Brandon. Okay, well, that's kind of high also, but let's see what happens. So go ahead and record the 8 newtons, and if both Tyler and Joseph still get around the mid to high 6s, go ahead and record that, but get the frequency that goes with it, because that might also be affecting it, why you're getting such different tensions, because your oscillator might be oscillating the string at a different frequency that I have, but the two together will ameliorate each other. And your length is around 76.5. Yeah, so if you get too long of a string, Brandon, then you have to accommodate, because that goes up, then the tension has to go up. Yeah. And Tyler, okay, I changed the length of motor in textbook to about 2 inches and got 5.5. Oh, you mean between the book and the motor? Yeah, that's another thing. If it's too long from book to motor, then that will affect the whole thing too. So you want to keep it kind of short between book and motor, because it'll flop on the other side and change everything. Maybe that's what's happening with Brandon. I don't know if Brandon wants to check the distance between motor and book and have it closer to like maybe a finger span away, but the motor not touching the book. See if that changes anything. Where is this to measure the string from? Okay, so for the length L, then you're measuring from the knot that you have holding the motor on the string, so the knot on the string for where the motor is at, to the knot on the string where you're tied off to the eye screw of the IOLab. That's your length L for the mathematical purposes. But everyone else is talking about how long should the string be from motor to book, which is clamping down the string. And that should be fairly short. And I got mine about an inch away, maybe a little less. Okay, so Matthew, can you pull up the image of how each node should look again, please? I can do that. And then Tyler, how do we get the graph that displays the mu number? You just plot the table that is on your Excel worksheet. You've got the F over n squared, and you have the tension T. You see that table on the worksheet? Just above where you're going to put the, yeah. So you're just going to click and drag across the data, because you're going to have f over n in a previous table, and then you take f over n squared and put it into that table that you're going to use to plot. Then you have your force values, which are your t's, and those are in the appropriate spots for n equals 2, n equals 3, n equals 4, and n equals 5. Then you just plot the data as a linear trend line. So try that and tell me what you get. Okay, back to Matthew. Okay, so here's n equals 2. N equals 2 has, like, one side is where the motor is tied, and the complete other side is where the IOLAB eye-screw is. Then you have 2 antinodes and 1 node in the middle, and that's n equals 2. And then, Brandon, so I shortened up the distance between the motor and the book, but it looks like the 8 newtons value. Okay, so stick with that. And then Tyler, and T values are the force calculated using probe. Yes, so the average force from the force probe, that's right. That's the tension T. Okay, so Matthew, do you see on the screen where I've got n equals 2 having 2 antinodes and n equals 3 has 3 antinodes? You see that? So is that your force, minus 1.5? Or, okay, try pulling more. I think you're getting I think the tension is too loose and your motor is giving you a false reading. So try pulling more and get it closer to 5 newtons. And you see that Brandon got all the way up to 8 newtons, and then a couple other people had like 6.5 newtons. So definitely head towards the 5 newton to see if you can get an n equals 2 standing wave to form. Okay, so you don't calculate the frequency, you get the frequency from the fast Fourier transform. So I can show you that again. I'm going to stop sharing my notes and bring back. Let's see here. Okay, so Tyler, if you've got your force, get rid of the RSSI, that isn't supposed to be there. Okay, so here's a force that I took earlier, and I see that I've got this, and I actually got the standing wave to form first, then I took data. So I'm holding it still, and so I'm holding it there, then I stop taking data after about 5 seconds, 4 seconds. Then I'll go ahead and do that, and you already have that. So looks like I have like my average like 5.8, so I'm kind of over 5 for that one. And then you go to here, where it has this little square with the arrow sticking out, and it says toolbar when you put your cursor on there. You left click on that, and then you move your cursor over to where it says FFT in the drop-down menu. Then you go down to the 1024. That's how many bins is going to get split up. Click on that, and now you have this graph down here, which has an x-axis of frequency. So this is a frequency axis. Then you put your cursor up on your data, and you can left-click on. Now don't left-click and drag, just left-click, and you'll be able to drag that around. And you can see I can left-click again, and it will set it. And I may have like a frequency trying to form here and other frequencies moving right here, but there's a single one that should be really, really tall. And so I'll put that black line in the center of that. And there we have that frequency is 224.65 for my data. It'll probably be different for your data. It all depends on what's vibrating on that string. So for me, I would have a force of 5.848 newtons and a frequency of 224.651 hertz. So hopefully, anyone else that has a question, I can pull this back up later if you have questions about getting the frequency. So I'm going to go back to my notes in that one drawing. Someone was still worrying about the how many antinodes for n equals 2, what does the waveform look like for n equals 3, what does the waveform look like for n equals 4. And of course, you just extrapolate for n equals 5 because you just have 5 antinodes. Okay, but here's the clue for you. For me, the n equals 2 was somewhere around 5 newtons of force. For the n equals 3, it was just under 2 newtons of force. And for n equals 4, it was under 1.5 newtons of force. And for n equals 5, it was just under 1 newton of force. So my data was everywhere from approximately 1 newton all the way up to approximately 5 newtons for 5, 4, 3, and 2 for the n's. So about 5 newtons for the n equals 2, about 2 newtons, actually it was a little less than 2 newtons for the n equals 3, and it was less than 1.5 newtons for the n equals 4, and it was just under 1 newton for n equals 5. Now yours might be slightly different, but it's definitely, from 1 newton and higher for the data. So if you're getting something like 0.6 newtons or 0.4 newtons, the string is too loose and it's giving you false readings. And in fact, when I was doing the n equals 4, it actually changed to look like an n equals 2. But I knew I was shooting for n equals 4, I could see it forming. But then once I got there, I guess it was just a little too loose and it looked like n equals 2, but I knew it was supposed to be n equals 4. So I still took the data as if it was n equals 4 because I was seeing it form. Okay. Okay, so Ben, so you said that we should not start measuring the force until we have a harmonic. That's my suggestion. You could, if you wanted to, just make sure you know which portion is actually the portion where you're holding the force still, because you might be all over the place. And when you actually stop taking data, it'll scrunch everything together. So it's up to you. If you want to do it, have the force probe turned on during the entire time you're looking for the harmonic, Or you can wait till you have the harmonic and take the data. It's up to you. I just like finding the harmonic first, then taking the data, because it's just one straight line. And when everyone is finished taking their data and they're done, make sure that you take the batteries out of the battery holder. Do not leave them in the battery holder. Don't store them in the battery holder. Take the batteries out and put them back in the bag that came in. Okay, so we started at 10:10, it's now 11:22, so we've been going for an hour and 12 minutes. And Matthew, I've tried to do a different length, recalibrate, and I'm still getting -2 for the second harmonic. Even if you pull even harder, Matthew, increase the tension. Now, I believe if you have -2 for the n equals 2, then you're not going to get good data. Unless have you tried recalibrating the force probe? Try that. Even though the string is tied to the I screw, go ahead and give yourself some slack on the string and set the iLab up for doing the force probe. Yes, I just keep recalibrating. Okay, so you did that. So I'm trying to think of what I can do here. So we have a little bit of time. Matthew, go ahead and put down the -2 newtons that you're getting, or actually just the +2 newtons. We don't worry about the negative sign for this experiment. And then go ahead and try and get the n equals 3 and n equals 4 and n equals 5. If you pull tighter, it's just going to a flat line. Well, how much force do you pull with? What's the largest force you pulled with so far? And then, Kimberly, how do we calculate the linear density again? That's from the slope of the line when you plot the graph. And the slope of the line is supposed to be equal to 4L squared mu. Okay, so Matthew, go higher than 4 newtons. Try around 5 or 6 or 7 and see if you can get it to form. And back to Kimberly, so you've got the slope. And then you divide the slope value by 4 times L squared, using your L, of course, in meters. And you should get the linear density mu. That's just from that equation we have here. You're welcome. So that equation right there. So there's the y, there's the x, and then 4L squared mu it represents the slope. And you have a numerical value of slope from the graph, and you equate that to 4L squared, and divide the slope by 4L squared, and you have your mu. Okay, Joseph, mine went flat right around 5 newtons, but if you keep pulling it, it should give you 2 oscillations. Yeah, that's what I'm trying to say to Matthew, that he just needs to pull stronger. Just don't go above 10 newtons. See, not linear. It's supposed to be, yeah, it's supposed to be linear. You want to share that with me, Brandon? And take a look at your Excel worksheet? So Justin, you would right-click on the equation itself, and there should be a drop-down menu that appears when you right-click. Then go down to Format Trend Line Label and click on that. and then go over to the right where the window opens up, and it should have category, and I'll probably say general. So change general to scientific, and then it'll give you the option for how many decimal places you want. I usually choose 4. You're welcome. Okay, so we have a little bit more than half an hour left to lab. So let's see. I don't see where I can share. Oh, maybe I didn't get you. Let me see. I was doing some people. You're right. I see. I have 3 people I didn't finish out because it was later. Let me just fix that. And you should be able to share now. Okay. I see what you mean. That's not right. So, can you click on the line that you have created there? Yeah. Okay, so there's that. Now go up to the plus sign on the graph for the add trend line. Yeah, you're already there. Yeah, add trend line. And you've chosen a linear. Let's try this again. Why don't you go ahead and delete the graph completely? Then go up and choose your values there. And then go up to insert. And choose the charts, the scatter graph. Not that one. No. Go back up to the, close that. Just close that window. Close that window. Go up to the scatter chart, one more down, that one. Click on that and choose the first one. And you still have that. All right, let me take a look at your numbers here. You have F over M. You have those. Oh, I think you've done something. I think I found it. I think. Let me see. Frequency divided. You see your F over N. The first 2 look, because you take the frequency divided by 2, you should get 100. Click on that first F over N box. And what do you have up there? D11 divided by F11. So it should be E11, not F11. Oh no, you're supposed to divide by, C11. So it's D11 divided by C11. Go up to you there. Yeah, F over N. So D11 over C11. They're not F, okay, then you have to change all the others. Does the force go in the cell dot? Where it says tension force T in newtons in that orange box. Now that looks a lot straighter, doesn't it? All right. So go ahead and fit a linear to that. Yeah, I understand that. I mean, okay, so Ben, did you hear what I said about the force going in that orange box above the area? It's on the far right above the area where you're putting your graph. So it should have, on the left-hand side should be like the F over N quantity squared. On the right should have the T. All right, you're welcome. Not good with minimal percent error. See you next week. Great, Joseph. Good to hear that. Make sure you take the batteries out of your battery holder. All right, thank you. You enjoy your week too, Justin. Take the batteries out of your battery holder. All right. And then Connor. Are you there, Connor? Let's see. How do we calculate F over N? Well, you take the frequency F you found divided by the harmonic number for that same one. And Connor, did you get my email? You're welcome. I just want to make sure you got that. So go ahead and use that. And yeah, use those screenshots in your report. I can show you it's not actually, it's for the linear density, but I can show you the equation. Yeah, let's see here. Okay, so down here we've got the linear relationship. We're calling it a linear relationship because we're just going to do it that way. So the tension T is the y, and the f over n squared is the x, and so what's left is the slope value of 4 times L squared times mu. So whatever slope value you get, Brandon, equate that to 4L squared mu, and then just divide your slope by 4L squared, and that should give you mu. So Ben, what should the frequency be for the second harmonic? I've seen people get everything from like 160 hertz to like 220 hertz. What did you get? You're welcome, Brandon. So Ben, what frequency did you get for the second harmonic? $177. Yep, I've seen that before. So go ahead and put that in. So all these frequencies that people are getting should be kind of close to the 200 hertz. You're welcome. Some will be a little bit lower than 200, some will be a little bit higher than 200, but they kind of range right around that 200 hertz mark. So Nathan, you're only getting standing waves at very small force values. Yeah, that shouldn't be that. It has to be, you should get the standing waves from like 1 Newton of force all the way up to maybe 8 Newtons of force, because some of you are getting 8 Newtons of force. So it's definitely over 1 Newton of force, Nathan. It might be, because I had one of my TAs do this, it might be that you are not,